In this example problem, we're going to compare two separate models that we could use in a business application to determine which one of them is a more accurate measure for the thing that we are trying to predict. In this problem, we have a data file that contains the information about the crew size of people that we had and their weekly output in terms of units for the last 27 weeks at a manufacturing firm. And our two possibilities are listed down here. The first model would just simply be that y hat equals BO plus B1 times X1. And that signifies a linear relationship, which means as the crew size increases, the output that they produce should increase proportionally. Model 2 is y hat equals BO plus B1 times X1 plus B2 times X1 squared. And that suggests that there's a quadratic relationship between these two, that it isn't a purely proportional increase, that if we graphed out the crew size versus the output that they have, we would have kind of a U-shaped return. Which one of these two descriptions more accurately fits the criteria? Well, to determine that, we're going to use the RMSE, the root mean square error. It is a measure of how far what your model would predict for a certain amount of output based upon crew size differs from the actual output from the crew size, and they call that the residual. So RMSE, the root mean square error, is basically the square root of all of the different residuals that you had for the information that you're working with. To use this effectively, we're going to separate our information into two separate sets. Yes, we have 27 returns. One of those sets is going to be the training set, and that's the portion of the information that you use to create the model. So the first 18 observations that we have here, we're going to use those 18 observations to make our model. The other remaining portion of the information is what we call our validation set. Those are the points of information that we're actually going to plug into the model created from the first 18 returns that we had to figure out what's the residual. From the model we created, what was the prediction, the y hat for that, versus the actual output that we made for each one of those. And that will allow us to figure out how badly our model is predicting numbers that differ from what actually happened. So we want to go through and figure out which model has the lower root mean square error. So the first thing that I'm going to do is figure out what regression equation 1 is going to be, the linear relationship between the two. Well, I can go to my data analysis toolpack and do that. And I want regression. So delete out the information that I had in here. We want to determine a regression model where crew size influences output, therefore crew size is going to be our X and output is going to be our Y. But we only want to use the first 18 observations or our training set to determine this. So what I'm going to do for our Y range is take the first 18 returns going up to observation number 18 for my Y range. Whoops, I'm in the wrong spot. Apologies. Let me go fix that situation. Put it in the right spot this time. There we go. Perfect. And since that's all the observations that we're using for our Y range, we got to use the same amount for our X range. I want labels on since I put them in the headers. And then down here, I'm going to put the output range below because I'm going to have to make a graph in this area. So I want to kind of stuff this off in a spot where it's not going to be in my way. I'm going to pick cell A30. And I'm going to hit OK. And the return that I get for my summary output that we have right here tells me that our intercept is 12.98 and some change. And our coefficient for crew size is 0.14 and some change. So essentially, hypothetically, a crew of 0 could make 13-ish units, but for every additional person you put on the crew, they can make about another 14 tenths or 1/7 of a unit. Let me go and grab those numbers and put them in to my linear regression. So that's going to be my B of 0, and my B1 is going to be the coefficient that we have for our crew size. For regression equation 2, I want to treat the crew size as though it is going to be a quadratic relationship. And to do that, I'm going to have to add another variable for the square of our crew size. So let's get a column going that's going to calculate that. And it's just equal to our crew size. So to the power of 2. So in this case, 2 to the power of 2 is 4. That's what 2 squared is. And I can do that all the way down the line for all of my returns. And just math check everything came out correctly. Yep, all those look correct. Those are all the squares of the crew sizes that we had. It's nice to work with small numbers. And now, just like I did before, I am going to use the regression tool one more time to find out what my B0, B1, and in the case that we have right here, our coefficient for x1 squared in this case are going to be. And I'm going to do it for the same sample set that I did before, the first 18 returns. So I'm going to go to Data Analysis Toolpack, back to Regression. I still want my Y range to be the first 18 returns that we have for output. But now instead of just column C for our X range, I want to have all of crew size and crew size squared for those first 18 returns. And I'm going to put that output over off the side of the other one. So I'll just pick a cell where things are going to line up nicely. I'll put it into, we'll say, K30. Sounds good to me. I did it again. Wrong cell. Hold on. We want to put the output into cell K30. And my X range is going to be the first 18 returns for crew size and crew size squared. Now when I hit OK, it should come out. But before I do so, I want to do one thing. I want to click this little button down here that says residuals. I'm going to use it later to prove a point. But for now, I want to have it in my return, so I'm going to hit OK. And when I do that, I get my return for our different inputs over here. I get the coefficients for my 3 different variables. And the plot at the bottom has residual output. I'm going to talk about that in a second when we get there. But for now, let's take these 3 numbers that we got, our 3 coefficients, and throw them into our regression equation. So the first one is going to be our constant of 1.88 and some change. The second thing that I'm going to have is the coefficient for crew size, which is 4.6806. And then for our crew size squared, I'm going to use that as the negative 0.3782. So that is our regression equation if we consider this relationship to be quadratic. Well, now what? Now how do I determine what the root mean squared error is? Well, what I can do in this case is find the difference between the observed value for that level of x, for the crew size, and what our model, either 1 or 2, would have predicted for those spots had we plugged them into that. So the observed value is the actual amount of output a crew of that size made. It's all of these numbers we have over here. In observation 19, the first observation that's in our validation set, when 2 people were on the crew, the observed value that they made was 9 units of output. And then I can just do that for the whole entire list of information that we have here. So all I'm doing is just copying down the actual amount of output that we had for the 9 different returns that are in our validation set. But what would, we're on model 1 right now, what would have model 1 predicted? Well, to do that, we can go through and we can just plug each one of those crew sizes into model 1. So over here, for model 1's first predicted value, what I'm going to do is I'm going to say that it's equal to this constant we have over here in cell G11. And I'm definitely going to want to fill handle, so I don't have to write this a million times, and I'm always going to be referencing these same 2 inputs for the formula, so let's go ahead and make that absolute. Plus, in parentheses, the coefficient for our x1 variable in model 1, which I'm also going to want to make absolute because I'm always going to be referencing that, times the x variable at that level. And the x variable we have at that level is what's over here in cell C20, the 2 people. Those 2 people made 9 units. So according to our model, if we had a crew size of 2, what predicted amount of output would they have made? They would have made 13.27 units. Much different than our 9. How different, in fact? Well, the 9 units that they actually made, minus the 13.27 that our model is predicting, is telling us that the residual, the actual difference between what our model predicts and what was the observed value, is negative 4.27. And with that in there and with the proper spots made absolute, I can fill handle. And here I get all of the predicted values and the residuals, the differences for each of the 9 points that we had in our validation set. And that is going to be enough for us to calculate out our root mean square error for model 1. The formula for it is given in this problem right here. It is equal to the square root, open a parenthesis, of the sum squared of your residual range, which is going to be all of these differences over here in column G, divided by how many residuals you have, which you can find by doing count A of that same range of information. So for our root mean square error of the first model, I can say that it's equal to the square root of, open a parenthesis, the sum squared, sum SQ, really undo that. I don't know why I moved. There we go. Square root equals the square root, open a parenthesis, of sum squared times the range that we're trying to square, and sum, which is the range from cell G20 all the way down to G28. Close that parenthesis. And then I'm going to divide by the count of what we have in there. I'm going to use the count A function to do so. So the count A of the same range. And I'm going to close that second parenthesis, and I'm going to hit enter. And when I do, it's going to tell me that I should add 2 parentheses at the end. I'm going to say yes, and it is going to return my RMSE to me, my root mean square error. And the root mean square error for model 1 is 2.5663, which is a fancy way of saying, on average, this model's residual difference from what it's predicting to what actually happened is about 2.5 on every single observation that we have. Let's do the same thing for model 2. We're using the same validation set. We're comparing apples to apples here. So we're going to want the actual amount of output for all of the different ranges that we have, just like we did before. So this column for model 2 should have the same exact numbers that model 1 had because it's the same observed value. And we are going to plug that observed value into the second formula that we created. So over here for the very first one, I'm going to say that this is equal to the constant for model 2 in cell G12. And just like before, I know I'm going to always want to reference this cell, so let's go and make that absolute, plus the coefficient for our x1 variable, also wants to be absolute, times, in this case, the number that we have for our input for this particular response. And for, just like before, for observation 19, the crew size was 2 people, found in cell C20, close that parenthesis, plus, I'm going to go through, I'm going to grab my coefficient for the x1 squared variable. I'm always going to want that to be the same number, so let's make that absolute. So you're always going to make your coefficients absolute in this problem when you're fill handling down, times the return that we had here. And you can grab this from wherever you wish. If you want to, you can say that it's the same thing to the power of 2, because it's x1 squared. If you wanted to, you could have used the information from the crew size squared and just clicked on it because you already have that there. Whatever works for you. I'm going to just use the thing and square it, and I'm going to hit enter, and that comes out to be 9.74. So this second model is predicting that a crew of 2 people can have output of about 9.74 units in a week. Well, how much is that different from what the observed value was? They actually made 9. We predicted 9.74. So their actual output was 0.74 units less than our model had predicted. And now one more time, I can go through and I can fill handle. And from here, I've got all of the returns that I had for our residuals for each spot. And looking at this right here, there's a lot of numbers that are a lot closer. I'm willing to bet just looking at the residuals that we have that our RMSE is going to be superior for model 2. But let's prove it. Let's do it in numbers. So I'm going to use that same formula that I had, this guy right here, to figure out what the root mean square error is for our second proposed model. And to do that, I am going to go and I'm going to start my formula up over here in the cell, that this equals the square root, SQRT, open a parenthesis, of the sum squared, open a second parenthesis, so sum SQ, of the range that I'm working in. That's going to be all of the residuals that we have in column J, so this is J20 to J28 in this guy, divided by how many residuals we have. That's the count A function, so I can go and highlight the same exact range one more time, J20 to J28. Two parentheses so I don't get dinged at this time at the end, and then I hit enter. And it comes back as 1.4282. So what that is implying right here is our root mean squared error for our second model, where we propose this relationship is quadratic and not linear, is only returning an average residual on each prediction of about 1.4 units, significantly lower than the 2.5 that we had for our root mean squared error from model 1. And that's a good measure of goodness of fit right there. We're getting a lesser residual. We're missing by less with our predictions by using the second model than we are the first one. So we're validated, sorry for the pun, that model 2 looks to be stronger than model 1. We can always back that up by using a more traditional method, in that case, our adjusted R squared. What was the adjusted R squared? I'll go grab it for the first model. Our adjusted R squared right here is abysmal. It's so bad. It is negative 0.0443. Very few of those actual returns we had would fit exactly on the regression line that was made by that first equation. Basically, none of the change that's happening in there can be attributed to the crew size that you have if you consider the relationship to be linear. But what if we consider it to be quadratic? Well, the adjusted R squared for that model over here, while not the prettiest thing in the world, is so much better. Rounded off, it is 0.5970. So about 3/5 of the reason that our observed value is coming through is due to the crew size happening if we consider that relationship to be quadratic, or 60%, if you will, of actual points will pretty much fall in line that our quadratic regression equation would make, or our regression equation would make, considering a quadratic variable. And speaking of, since this number is negative for a square, I know that's an upside down U shape. What does that imply? It implies that production increases at a pretty exponential rate when your crew size starts going up until you get to a certain point. But once you get past that point, you have very large crews, the returns aren't as good. And it kind of makes sense if you think about it. Doing something by yourself is hard. Having a second person to help you helps. Maybe having a third person there will make you even better. But when you start getting into 4 and 5 people, your output for how much you're going to make isn't going to keep increasing proportionally. And then if you get to a point where you have like 15 people sitting in the room trying to do something, you're all going to be trying to go to the same machines. You're going to be running into each other. And your additional output in no way will ever be linear. So an upside down parabola, if you will, makes a ton of sense in this case. Crew size, the number of people that you put on there, there's a sweet spot. You want to have a perfect size crew, and that would be the vertex, in this case, of your quadratic function. So last thing before we end this video is earlier I had this particular regression equation make me a return over here for the residuals that we had in the certain spots. And if you'll take a quick peek-see right here for the first guys that we had, you're going to see that the residuals that we have up above are exactly the same number from our predicted value there to the residuals that we had out here for each given observation. You can use the residual button to automatically calculate your residuals, and if you want to do so, feel free to do so. But I decided to do it mathematically first just to prove that it works, and you know how you would use the formula to calculate a predicted value. But if you turn residuals on in your data analysis toolpack when you're doing this, it will give you the predicted output for the equation that it's making automatically, and will give you the residual from each point between what happened and what its actual value was.